So hello everyone, so welcome to our this week Rutgers Efficient AI seminar talk, and today we have the Professor Cong from the Gentech to give this talk. And Professor Hao is currently assistant professor at the Department of the Electrical and Computer Engineering at Gentech. She was a postdoc fellow in EC at the UIUC. She received her PhD degree in electrical engineering from the Waseda University, Japan, and the master and the bachelor degree from the Shanghai Jiao Tong University, China. Her primary research interest lies in the joint area of the efficient hardware design and machine learning algorithm, and she's passionate about reconfigurable and high efficient computing and building useful electronic design automation tools. So now let's welcome Professor Hao to give us this talk.
All right, thank you very much for the nice introduction, and hello everyone. My name is Kelly. This is really my great honor to be invited here to give this talk. So the title is about graph neural network and reinforcement learning in electronic design automation and beyond. I know this is a very large talk. This is a very large title, and what we have done is just initial exploration and some preliminary work. But the more important purpose of this talk is that I want to introduce to you this interesting research area, and I want to uncover some of our findings so that maybe we can attract more researchers and we can work together in this interesting area. So this is something I'm gonna cover today. So first I will give a brief background about what is graph neural network, what is reinforcement learning, and what is high-level synthesis, in case you're not familiar with that. And then I'd like to introduce two pieces of our previous work. So they're all about high-level synthesis, and they're defined as program-to-circuit problem. So the first piece of work is IronMan, and the second piece of work is program-to-circuit. And then I would like to briefly discuss the extension or the future opportunities for this topic. And we believe that this program to circuit can be extended to program to X, whatever this X is. And we really want to attract you and attract more researchers into this interesting topic and area. So I would like to acknowledge my collaborators. They're all amazing, especially my first author, Ms. Wu Nan. She's from University of California, Santa Barbara, and I think she's also in the audience. And without their excellent help, we couldn't achieve this research result. So thank you very much for all the insightful discussions and hard work. So let's go into the background first. What is graph neural network? A very brief introduction. I think we're all very familiar here with traditional neural networks. And these traditional neural networks, they're designed for simple sequences and grids. For example, we all know ImageNet, we all know images very well, and these can be represented as grids, and then we can apply some some convolution neural network, and then get some results. Or the inputs can be speech or text, and in this case, we can reorganize them as a sequence, and then we can apply some famous sequence-based model like LSTM or transformer in the future. So these are some things that we're very familiar, and these are the inputs that are well aligned into sequences or grids. But in reality, a lot of real-world data, they're not well behaved. They do not live on these grids. For example, we can see some figures here. The first one is a social network, the second one is an economic network, and the third one is a protein interaction network. And we can see these graphs are very complicated and they're not very well aligned. So these graphs, they have arbitrary size and they have complex topology structures, and there's no fixed node ordering or reference point. So every node can be the root node, every node can be the node of interest. And also, these graphs are often dynamic and have multi-model features. So this makes the problem even more harder. And generally, the traditional machine learning algorithms working on well-aligned grids and sequences, they don't apply to this complicated real-world data. So this is where that graph neural network is going to play a role, and a very important role. So for graph neural network here, the main idea is that we want to pass messages between pairs of nodes and then aggregate them. So for example, here you have an input graph. It's not a grid, but it's as a graph structure, and then we do this message pass between node pairs along these edges, and we do the same thing for each node here. And then we pass these nodes to an activation layer, and then we do this again and again. And finally, we can get some output. So this is the overall big picture of how graph neural network is done. And this is the more detailed implementation of graph neural network. So here, the key idea about graph neural network is to generate node embeddings based on local network neighborhoods. For example, here, this is the input graph, and this is the nodes that we're interested in. And here, for each node, there is a node embedding. So node embedding is basically a vector to represent the node features, for example, here. And every node may have very different node embeddings that representing their different features. So this is the input graph with node embedding, and this is the local network neighborhood. This is the node of interest. And this is the computation graph for this node of interest. So for example, this node A has neighbor B, C, and D. So here it aggregates information from B, C, and D. And then B also has neighbor A and C. So you can see here, A and C. Okay, so B also aggregates information from its neighbors. And inside these black boxes, we typically apply some transformations, and multi-layer perceptron is one popular choice. So this is how graph neural network can be applied on the graph inputs, and this is how the computation can be done. And the good point, the good feature about graph neural network is its inductive capability of graph neural networks. So one important feature is the graph neural network model parameters are shared for all nodes. So it first reduced the amount of parameters, and second, because the parameters are shared across all nodes, they're not distinguished. So that means the model can generalize to unseen nodes. And even better, it can generalize to entirely unseen graphs. For example, here, your graph neural network is trained on this structure, but it can just generalize to a new graph that is totally unseen, and also, of course, some new nodes. So this is one very nice feature about graph neural network, and I think this feature is very useful in solving a lot of domain-specific problems. For example, especially EDA problems, we don't have a lot of training data, so we train on some set of the graphs, and then we just generalize to new graphs, and it can save a lot of time to solve new problems. Okay, so this is the background about graph neural network, and now we take a brief look at the reinforcement learning. I think most people might be more familiar with reinforcement learning, and so this is only a very brief introduction. That reinforcement learning means there is an agent learns in an interactive environment by try and error using feedback from its own actions and experience. So here is an agent, and it will interact with this environment by taking some actions, and this environment will provide some reward to this agent. And then based on the action and the environment, the state will change. And based on the state, the agent will take actions. So this is the overall flow of the reinforcement learning. And the good point about reinforcement learning is it is suitable to handle control problems or sequential decision-making processes. And also, in terms of the design space exploration, which we care a lot in our EDA domain, that it can explore design space proactively and intelligently. So that's what makes reinforcement learning very popular. And also, the agent behaviors are optimized by embedding optimization goals into this reward function. So whatever your optimization target is, for example, you're designing a circuit, you want to optimize the area, you want to optimize the wear length or power, you can embed those optimization goals into this reward function. So it's very flexible. Okay, so this is the background about reinforcement learning. And the third part, the third piece is high-level synthesis. I think high-level synthesis is also a well-known term. A lot of people should be familiar with that. So high-level synthesis is one step, or usually the first step within this software to hardware translation, this synthesis, overall synthesis flow. So if you have a software program, you have some specifications, you want to produce some circuit design. Either it's an ASIC or it's an FPGA. The first step is usually high-level synthesis, that it allows you to start from high-level behavior description like C and C++, Chisel, and you go through these high-level synthesis tools so we can have some lower-level description like Verilog and VHDL. So this is the overall idea about high-level synthesis. And the reason we like high-level synthesis is because it can really provide an easy programming environment that a lot of comparing with C, C++, and Python and Verilog, I think a lot of us will prefer C and C++. And this Verilog is sometimes very intimidating. So the first advantage of HLS is, of course, it reduces a lot of burden for circuit designers. And of course, it's usually faster to use C and C++ comparing with using Verilog. And it's very important to improve the productivity using high-level synthesis. And of course, it relieves the burden from a software programmer, and it can promote device usage. For example, if you can program the FPGA using high-level synthesis, it's much easier than using Verilog. So more people will be more willing to use FPGAs. And of course, the most important one is using high-level synthesis can reveal more optimization opportunities at a higher level. So when you're doing optimization, the higher level it is, the more optimization opportunities you have and the more impact it has. So high-level synthesis is very useful. It promotes productivity and resource and device usage, and also provides more optimization opportunities. So that is why we're still interested in this high-level synthesis topic. So now this is the background introduction. What is GNN? What is RL? What is high-level synthesis? And now let's take a look at our problem. So we will introduce this high-level synthesis. It's essentially a program to circuit problem. Right. So essentially, we can regard this high-level synthesis as a program to circuit problem. For example, here we have a program written in this way, and these programs can be translated to data flow graph like this. This is the data flow graph, DFG, the computation pattern. These can be regarded as the intermediate representation, or short for IR. And this IR is a very common term in compiler. So these programs are translated into data flow graphs, and then these data flow graphs, based on this data flow graph, we can apply some traditional high-level synthesis technologies such as operation scheduling, resource allocation, resource funding, and so on. And then these data flow graphs can be translated to this register level, register transfer level. For example, this can be written in Verilog. And this is not the final circuit, but it describes the circuit, or we say it's a descriptive language for the circuit. It's already very close to the final circuit. So this is the high-level synthesis that we can regard these high-level synthesis as the procedure of program to circuit. Here we have a program, and then we jump to this circuit. So this is the problem of program to circuit. And here, of course, this process has a lot of challenges. It's not easy. And still, it has been studied for a couple of years, many years. but still there are some remaining challenges that people are still working on. So today we're going to highlight 3 of them. The first is hard to predict RTL circuit quality, and the second is multi-objective trade-offs, and the third is manual code transformation. And I will introduce them one by one. So first, what does this hard to predict RTL circuit quality mean? So this is the overall flow from the program, the real program, down to the actual implementation. It can be a circuit, it can be an ASIC or an FPGA program. So this is the actual implementation that people can really see, or to fabricate or to use that to program FPGA. So this is really the end product. So within this procedure, from program to data flow graph, this is very quick. It only requires a few seconds using the compiler front end. And then from data flow graph to this RTL circuit usually takes minutes to hours, depending on how large your design is. For example, if you're using high-level synthesis tool, if you have a very large design, it can still take up to hours. And then from this RTL description, using Verilog to achieve the final actual implementation usually takes hours or maybe even days if you have a really large design. So each step is going to take more and more time. It's going to be more and more time consuming. So the observation here is getting the actual circuit quality after implementation is very time consuming. So here, if you want to get the actual implementation performance, that how is your circuit working, what's the area, what's the latency, and what's the critical path, what's the maximum clock frequency you can achieve, to get this actual circuit quality after implementation is very time consuming. If you want it to be accurate, you have to run through the entire procedure. So of course, we want to think about how about we do some quality prediction. We don't run it, but we want to predict it. So of course, we can do that, but we have observed that this RTL design quality is really hard to predict, especially for irregular data paths. And we have already observed that these existing high-level synthesis tools, their estimation sometimes can be far from accurate. And we were going to show that in later experimental results. So these tools, sometimes they can do a good job, but sometimes they're not that excellent in estimating the real implementation performance, and sometimes can be far from accurate. And we also have some existing excellent work that are analytical model-based works. These predictors, sometimes they also work very well, very fast and accurate, but these works only work for well-structured data flows, that you have a well-structured computation pattern, for example, some nested loops and some recursive repeated functions. These works, this analytical model works for these well-structured data flows, but they're not good for irregular data paths. And also, we also see some recent machine learning-based predictors, and they require abundant features so far after the design synthesis and or even after during implementation. It means these ML-based predictors, they sometimes require some information from this stage, and sometimes they require information to be extracted from this stage. So they can be accurate, but still they can be very time consuming because you still need to go through this procedure to some point until you can extract these features. So this motivates our first thinking that can we do something like this? Because this is really fast. So can we just extract the data flow graph here? We stop here, and then we predict the implementation quality really accurately. So we can skip these 2 steps, which are really time consuming, and directly predict the implementation quality. And we also want it to be accurate. So this is our first motivation. We really want to predict the implementation quality accurately at a very early stage here. So this is our solution. It's not very hard to notice that this is a data flow graph, right? So it's a natural graph structure. So it's very natural for us to think that maybe we can use graph neural network that can be applied onto this data flow graph. And the good thing is, as I mentioned earlier, that they can generalize to unseen programs, which is also a very nice feature. So this is our first solution that we want to think about how can we use graph neural network here applied on the data flow graph and to predict the implementation quality accurately. So let's say we temporarily, for now, solved the first challenge. And now let's take a look at the second challenge. So the second challenge is about multi-objective trade-offs. Here are some examples. These are only examples, of course. In real cases, we have a lot more different choices and constraints. So for example, we have the constraint that the number of DSPs on FPGA, we just want it to be 2. We just only want to use 2 DSPs. And now our design choices is for each multiplication, either we can use DSPs to implement or we can use lookup tables to implement them. And these are the design choices. And our objectives, of course, we want to meet the user's specific constraint that we have this constraint. We have to meet it, right? We have to honor this constraint. This is the first one. And the second one is, of course, we want to minimize other resources, for example, number of LUTs and also the area and also the congestion. And the third is we want to optimize critical path timing, which directly affects the clock frequency. This is also something we want to optimize. And let's see, there are multiple design choices and there are also multiple objectives. So this is one example that this is the HLS default solution. That, for example, we have 4 multiplication and finally want to do this addition. So these yellow dots are operations using DSPs and these blue dots are operations using LUTs. So in this case, in this default solution, we're using 4 DSPs and the overall latency is 3, right? So it's 3 clock cycles. And this is another design choice, HLS solution with naive constraint that we can make a hard constraint. Okay, DSP is there's only 2 DSP, but in this case, we can see that latency increased from 3 to 4. So this is an alternative solution, but do we have a better solution that we can keep the constraint, but do not affect the latency? So is it necessarily true that we have to sacrifice the latency, the number of clock cycles, if we want to minimize or if we want to honor the user's specific constraint? So actually the answer is no. We have another design choice. Maybe it's a better choice depending on your optimization goal. So we can see that in this case, these 2 operations are using DSPs and these remaining operations can use LUTs. And in this case, of course, the requirement is that suppose you have enough LUTs and here is the trade-off, right? So in this case, we can see we are only using 2 DSPs, but we can still achieve latency to be 3. So this is sometimes can be a better solution. It honors the constraints, it doesn't sacrifice the latency, and sometimes we can also optimize the critical path timing, and I will show you later. So this page shows that we have multiple design choices, and there's always a better choice if we don't rely on the HLS naive solution. So these motivate us that how can we find or how can we design an automated DSE, design space exploration engine that can automatically find a best resource allocation, just in that example, to find a best resource allocation that we want to learn how to assign these resources, whether to give it a DSP or to give it a LUT. And we want to, of course, first meet user-specified constraints. This is a hard constraint. And also we want to trade off between resources and critical path timing, and I will show you later. And then, of course, we still do not want to sacrifice latency. So here, for example, we have a DSP constraint of 2, but we really still want the overall latency to be 3. So this is the second motivation. And naturally, we can think of, okay, maybe we can try to use reinforcement learning in this procedure to solve this problem, because we can regard it as a sequential decision making, right? We can assign these node by node. And this response learning can learn how to make these smart decisions and how to optimize the resource and critical path timing. So this is the second motivation and our solution. And what about the last one? The last one is sometimes we have to do some manual code transformation. Let me show you another example. So we like high-level senses because it provides high-level abstraction in high-level senses. And in most cases, we really like it because it makes our life easier. But at some cases, it can also conceal optimization opportunities. That, for example, structured high-level senses coding style will hinder this fine-grained optimization. It only can be applied to loops and function calls, and sometimes we really want to break these things to make more aggressive optimization. And also, irregular logic will require manual or complicated code transformation. And especially when you have specific constraint, this will further complicate the problem. Let me show you an example. Here, this is a very naive, cooked up piece of code. So this is a very natural case that a lot of people are seeing, that what if the current DSP constraint is only 3, that you're not allowed to use 8 DSPs, you're only allowed to use 3 DSPs. Can we achieve this efficiently without doing anything else using HLS tool? So let's see, let's observe that. So if we do nothing, the original solution is, okay, it uses only 1 DSP and it takes 17 clock cycles. And if we do some unroll, we can specify the unroll factor, right? So either it's a complete unroll or it's factor 4 or it's factor 3. And we can see that in this naive HLS, or let's say the default HLS solutions, the best we can get is, okay, we can use 3 DSPs, but the number of clock cycles is 8. These are produced by Xilinx HLS tool. So this is what best we can get, 3 DSPs, 8 clock cycles. But are we happy about this result? Probably we can do better. This is something we can do, that we can apply this code transformation, let's call it CT. This is how we apply the code transformation. And this is the transformed code. And it seems very simple, right? We just unrolled the loop and rewrite the program here like this. So after code transformation, we can see, okay, now we're using 8 DSPs and the number of cycles is 2. It's completely the same with this unroll, right? So probably you're gonna wonder, what's the point? Why are we doing this? Seems useless, right? So here is why. After we do this code transformation, we can apply some more interesting optimizations using this resource allocation. So after code transformation, we can apply this resource allocation program or directive to specify which of these operations will be used will use LUT to compute multiplication. So there are different cases we have tried, and we can see that now we can absolutely do better. In this case, we are using 3 DSPs, and we are also achieving the number of clock cycles to be 2. So this is the best we can get if we can do this code transformation. And of course, there is one trade-off that we have noticed, that this number of LUTs is increased. So there's always a trade-off here. We're not saying this is absolutely the best solution, but maybe at some point it can be better. And let's do a comparison that, okay, compared with the best case without code transformation, we can all have 3 DSPs, but apparently we have a much shorter number of clock cycles. And also we can notice that this critical path timing is also increased by a lot. And this is also significant. It almost allows us to double the clock frequency. So it means that the code transformation is actually providing a lot of optimization opportunities, which was originally concealed by the high-level abstraction in high-level senses. So this is why we like this code transformation. And of course, we can do that manually, but it will be cooler if we have something that can do it automatically, right? Okay, so this is the third talent. And this is only a very simple example. What if in real case we have a more complicated design and we have a more complicated constraint? Let's think about this. This is a little bit more complex nested loop. And there are some weird values here. Well, it can happen in real cases. And what if we have 13 DSPs? So this kind of thing will complicate the problem. And in real cases, we're probably going to see a lot more and more annoying constraints. So by facing these types of code and optimization requirements, that we really sometimes we need better performance and we need more flexible optimization choices. And our solution is, of course, we can try to do this code transformation. Okay, so this is the third motivation and the challenge that we really want to do this code transformation at some point.
Hello?
So this is, yep.
Yeah, I think we have a question from the audience. Do you want to answer that question right now?
Oh, okay. So I see. Okay, the question is the code transformation is for C, not to Verilog. If it's for C, the optimization can be performed at IR, not the code. Yes, the code transformation is for C, not in Verilog. And that is also true. That is also true that this sort of optimization can be performed at the IR level. And I think this is a very good point. Actually, we are considering that maybe we don't manipulate the source code and we extract the data flow graph and we can just change the flow, the graph, right? And that is also very natural that maybe we can try something interesting using graph neural network or reinforcement learning to manipulate the intermediate IR. And that is also another interesting topic that I'm thinking of. And yes, so in general, in this case, the code transformation is for C. And definitely, I do think for C, the optimization can be performed at the IR level. Okay, thank you. So then this is the motivations we observe. This is the solutions we propose. And then let's put them together, put them all together. So we propose this IronMan. This is an GNN-assisted design space exploration in high-level synthesis via reinforcement learning. And let's see, how are we putting them together? Okay, so this IronMan is an end-to-end framework integrating code transformation, a GNN-based performance predictor, and reinforcement learning-based multi-objective DSE here, targeting high-level synthesis. And it can be it's also defined as program to circuit problem. So let's break them into parts. So for the code transformation, it solves the third challenge, and it is motivated by manual code transformation requirements, and it can expose more optimization opportunities. And the second one, this GPP is graph neural network-based performance predictor. It solves the first challenge, that hard to predict RTL quality, and it can also act as implementation quality prediction. And the third part here, this is the reinforcement learning-based multi-objective design space exploration, and this RLMD solves the second challenge, that we can explore multiple object trade-offs and we can enable an automated DSE. So this is how this IronMan interact with the HLS tool. So the HLS tool will extract the HLS IR, and then we go through this entire procedure, and then we will output the transformed C and C++ with optimized directives to the HLS tool. And then the HLS tool will, of course, interact with the general input and output. So here, the goal of the IronMan here, of course, it's just a case study, and we're looking for more application use cases. So here, the IronMan goal is we want to find a solution that can strictly meet DSP constraints, and also can find Pareto solutions between DSP and LUT resources or IPG without sacrificing the latency. So let me break down into parts to see what's really happening inside. So this is the graph neural network-based performance predictor. We can see here, this is the overall architecture of the graph neural network. So the input is a data flow graph and the node features. And here, first, we're applying graph convolution neural network, and then we get the node embedding here. And then, because we're doing graph level prediction, so we have to do a graph pooling to get a graph representation. We're not focusing on specific nodes. We're focusing on the entire graph. So we're doing a graph pooling to get a graph level representation, and then we go through some multi-layer perception, and we get the predicted output. So here, this part is to generate graph representations. And this part is that we feed the graph representation into feed-forward neural networks. And here we're using 3 models of the same structure to separately predict these 3 resource and the critical path timing, the LUT, the DSP, and the CP. And here, the node features, we are manually designing these node feature vectors to indicate either this input is an output, what is the operation type, and what is the bit width, and whether it is applied the pragma. So of course, I think we already know that the goal of this GPP predictor is to provide graph embedding of DFGs, so it can generalize across different graphs. And also it can provide high accuracy performance predictions, and it can enable very quick evaluation of generated solutions and accelerate RL training. So the GPP is equipped together with this RL. Now we move to the second part, take a look at this RL engine. So here, this is the overall flow, overall overview of this RL engine. That for this RL agent here, the input is an unassigned data flow graph, and it will step by step, or we say node by node, to assign the pragma to each individual node, and then until the DFG is completely assigned with proper directives. So here, the state is every possible partially assigned data flow graph. The action is, of course, whether to assign a certain directive to the current node or not. For example, in this step, we are looking at this node and we make a decision. Do we assign it or do we not assign it? And the reward is a negative weighted sum of the predicted resource utilization. It depends on what you want to optimize, and of course, you can tailor and customize your own reward function, whether you want to optimize a lot better or you want to optimize the critical path timing better. So this is putting everything together. This part is graph neural network-based predictor, and this part is the reinforcement learning. And in this case, we are exploring 2 policy optimization methods. The first is actor-critic, the second is policy gradient. So for the RL architecture, so this part is the actor, it outputs the probability distribution of actions, and this part is the critic, state value function. And this is only used for actor-critic policy optimization method. And here is the reward. Here, it takes the predicted resource to compute the reward function. So this is to put the graph neural network and the reinforcement learning together. So now let's see how it works. This is the experiment setup. Let's see how the IronMan works on synthetic data and real world data. So we have around more than 4,000 graphs from synthetic data sets that we generated the data flow graph automatically just to train the graph neural network. And we also extracted 800 graphs from this real case world, this real case benchmarks. And our baseline is some heuristic algorithms, SA, GA, and PSO, and also the commercial Vivado HLS tool. And for training, we tried to train on some synthetic topologies and also some real case benchmarks. So in total, more than 4,000 graphs, and we evaluate on the rest of the graphs. So on the rest of the graphs, they include both synthetic graphs and real case graphs. And the evaluation is that the ground truth values and those resources are synthesized by Vivado HLS and implemented by Vivado. And we are thinking of the actual resource utilization and critical path timing. That is after the implementation. So it is not an intermediate report generated by tools. It's an actual resource after the entire implementation. So these values are really accurate. These ground truth values are really, really accurate. And also we will open source these sort of data sets. So if you want to play with it, just feel free to grab it. So let's see how this graph neural network, this GPP works. So first, this GPP will predict on resource utilization, including LUT and DSP, and critical path timing. So this is LUT, this is DSP, this is critical path timing. And this green dot, this circled in green are GPP predictions. If it aligns better with this diagonal line, it's better, right? So we can see that GPP is much more closer to this diagonal line than the commercial HLS tool, especially for the critical path timing. This HLS estimation is way off. So in general, the GPP is able to reduce the prediction error of Vivado HLS by 10 times in resource and 5 times in timing. So, and also we can see actually GPP works very well, not only for these synthetic data, but also work well for this real case data. I think right. So these green dots are synthetic data flow graphs, and these red dots are real benchmarks. So we can see the training data, the synthetic data only lines here, but the real benchmark data, they are aligning here. So it really shows that GPP is able to generalize across different graphs and across different graph size. So I think this is very promising. Also, the similar trend can be observed here. So this is the synthetic data flow graphs, and these are the real case data flow graphs. So it really shows that GPP or graph neural network is able to generalize well. And also we did a little bit design choice exploration that we tried different numbers of layers, and we noticed that, okay, 2 layers of graph neural network is the best. So we're just picking that. It means that maybe we do not need to stack a lot of layers to, maybe the too many layers will invoke this over smoothing problem, or it will mix up a lot of unnecessary information. So, and also let's take a look at the IronMan evaluation, how it does to generate this Pareto solutions. So there are 2 example applications that these dots are generated by heuristic solutions. These dots are heuristic algorithms. And these 2 dots, these 2 lines are the Pareto solution generated by IronMan. So obviously that we can find better Pareto solutions comparing with these heuristic algorithms. So in general, IronMan outperforms this heuristic method by a large margin, more than 12%. And also the fine tune also helps. We can see that these green dots are fine tuned, and these gray dots are also fine tuned. So, okay, this is more obvious. This green is fine tuned, this gray is fine tuned, and these purple and these blue ones are not fine tuned. So this fine tune really helps, and it doesn't take a long time. It only takes a couple of minutes. And then in general, we also observe an interesting thing that this general policy gradient outperforms actor critic. So that's a little bit out of expectation, because this actor critic is generally considered as a more advanced algorithm. So we have this discussion in the paper, so if you're interested, you can take a look. And finally, we are showing that, okay, this RMA is really good at trading off between multi-objects. So if we can just freely or flexibly assign different optimization functions that if we are more cared about this critical path timing, we can get a better timing result. Let's see here. This is around 8, 9, and here this is obviously a worse timing compared with this situation, right? Because we are setting this critical path timing more important. And of course, we can set other goals to minimize the number of LUTs. And finally, let's see how this RLMD can meet user-specified constraints. And this is also important that you have a user constraint, you have to honor it, right? So we can see this RLMD meets user-specified constraints almost perfectly. That it's almost more than 90% of the time, it can perfectly meet user-specific constraint, like in these cases. And compared with other solutions, with other heuristic solutions, they can only meet user-specified constraint in less than half time. So this is not good. I think the user constraint should be the top priority when you're trying to optimize your design, right? So this also shows that RL and equipped with this GNN can better predict and can better control whether it can meet the user-specific constraint or not. So this is a brief summary of IronMan. That independently, we have this GPP predictor. It can achieve high prediction accuracy, and we have this reinforcement learning algorithm that can obtain Pareto solutions that can outperforming the heuristic algorithms. And integrated together, this IronMan can help HLS tool to generate higher quality solutions under user-specific constraints, and it can perform flexible DSEs to provide Pareto solutions, and it can also find solutions that perfectly matching various DSE constraints, and it's of course much faster than the heuristic algorithm and HLS tools. Okay, so this is the brief summary of IronMan, and let's see what can be done next. This is not the end. So this is the only purpose I want to give this talk is I think there are a lot of upcoming, there are a lot of follow-up works that can be done. So let's see what's happening. We have observed some interesting things. So next is we are going to generalize it more. Program to circuit. We want to explore this GNN's its powerfulness for program representation and circuit translation. So how powerful it is it good enough or still not? Okay. So we want to dive deeper that for this general program to circuit problem, how powerful are the GNNs to represent programs and to solve this program to circuit problem here? Is it good enough or not? So that's why we extended our RLMD to this program to circuit exploration. That RLMD is really a very initial exploration. So in real cases, things are much more realistic. That we are considering all types of operations in the data flow graph. Some of them are even annoying that we not only have arithmetic computation, we also have memory operations, we also have controls, we have loops and branches. So these are a lot more realistic. And also we not only consider data flow graph now, we're also considering the control data flow graph, which is more complicated. I will show you later. And of course, we're going to need more complex learnable node embeddings, and we explore multiple types of graph neural networks. So in this case, we only tried a 2-layer graph convolution neural network, and now we explored different types of GNNs to see which performs better. So this is the observation. This is the observation that we observed 14 of the different graph neural network models. These are the models that we explored. And first we can see that these are the DFG results and these are the CDFG results. And comparing with DFG and CDFG, we can see obviously that this is the prediction error. So apparently the prediction error is much higher on CDFG comparing with on DFG, especially for, let's say, this lot. These are around 15%, and this is obviously around 30 or 20 more %, right? So this is the first observation we will show you later. And also we observed, okay, there are 2 winners here. The PNA model and this RGCN model. is generally outperforming comparing with others. Are there any insights or are there any reasons there? We are going to discuss that. So the first observation, comparing with data flow graph and control data flow graph, where the control data flow graph is more common if we want to consider the entire program, right? So in our observation, that control data flow graph size is approximately twice as large as DSG. So of course, it's more difficult for graph level regression. And also a major important reason is the CDFG has a considerable number of loops, and that can really challenge the representation power of GNN. So for example, this is an example DFG. This is an example CDFG, and we can see this is a loop. This red dots, this red lines indicates a loop. And we observed a lot of loops in the CDFG, and I think that's for sure. And this is the histogram of the loops. We can see more than half of the CDFG has loops. And also the loop length is also very interesting. That a lot of them, the loop length is around 10 or 20 or even longer. So we even observed like hundreds of nodes in the loop. So I think these kinds of loops and multiple loops is really challenging GNN. And also the control nodes and control edges also introduce additional complexity, because if we're doing the resource prediction, those control nodes, sometimes they don't directly contribute to the final resource. So that also makes the things very complicated. So that's why we want to call for more GNN related research to dive into this area, see if we can do a better job. And we also have two winners, as we introduced earlier, that the two winners is PNA and RGCN. So this PNA is multiple aggregators here. This is the principal neighborhood aggregation. So it means it has multiple aggregators that maybe it's a min, it's a max, or it's a summation. And these multiple aggregators, we think it's more powerful to characterize different neighborhood information. Especially in our CDFG, there are different types of edges, connections, and different types of neighborhood nodes. So this PNA might be very helpful in this case. And also the second winner is RTCN, relational information is important. So this is an illustration of the relational graph neural network, graph convolution neural network. It means it takes different relations into consideration. For example, in our case, some edges are data dependence edges, some edges are control edges, some edges are just memory operation edges or function call edges. So maybe identifying these different relations and different edges might be helpful in predicting the final quality. Okay, so this is 2 cents of our observation that this PNA and this RGCN is generally outperforming, and these are the reasons that we can think of. And the third observation, interestingly, is global information versus local information. That we can see actually, although the CDFG behaves generally worse than DSG, but the CP critical path timing is actually showing lower error rates and better consistency between DFG and CDFG. So our hypothesis here is that the critical path timing is some local information, because we only need to characterize the sensitive logic between two flip-flops, right? And this sort of local information is insensitive to graph size because because it's a local information. And on the contrary, the resource is some sort of global information. So we're gonna need to consider the entire graph. So that's why the global information is more sensitive to graph size. And that is why we're doing better in the critical path timing prediction, and also has a better consistency. I think that's very important because generally critical path timing is considered to be hard to predict. So this is the more comparison between the graph neural networks and the HLS tools. We can see that this is the relative error in DSP prediction. Well, generally, we can see that, okay, these triangles are HLS and these stars are PNA prediction. Well, they are comparable. They're not doing a lot better, but they're not even worse. So this is for the error in DSE. But for the timing, we can see actually HLS prediction is much better. It's much better than the, oh, okay. So the relative error, yeah, of course, the DSE, the HLS prediction is doing worse than graph neural network. The lower, the better, right? So this actually is very promising, and we're happy to see this result. GNNs are slightly better in resource, but obviously better in critical path timing, which is really hard to predict. And this critical path timing, I think it's even more important than resource because this is really something sensitive and cannot be directly predicted from the early stage. So I think this makes a lot of sense to use GNN for CP timing prediction. So these are the observed challenges so far, and of course there are some more interesting topics and challenges here, so that's why we think we need more researchers in this area. And we want to discuss the generalization across graph sizes, across node degrees, and out of distribution cases, and how can we invent the structure and algorithm innovations to process heavy loop graph topologies. So currently, those graph neural networks are not very strong, not very powerful in loop graph topologies. But in our cases, we have a lot of loops, right? So I hope something can be done to this one. And of course, we're also exploring, and hopefully we can do this together. And also, there might be a gap from classification to regression. So the most existing GNNs are tested or majorly designed for classification tasks. But our case, the resource and timing prediction is actually a regression, and we believe it's a harder problem. So we are going to need more profiling or testing to test whether the gap is large or obvious for classification, and our case, the regression. So these are the observed challenges so far. And finally, there's only one slide I want to talk about is this. There are a lot of more interesting research topics that can be extended from program to circuit to program to X, whatever this X is, right? So here, currently what we're doing right now is inside this block, right? So we're taking the high-level senses, the input is C, C++, we're using DFG and CDFG as the IR, and we are doing the downstream task in EDA, like we're doing the circuit translation, and we did a little bit design exploration. So this is the problem of program to circuit. But we believe there is a large family of the whole family of program to X, whatever this X is, that here we already see some existing works. They're using this IR from different IR formats to perform this performance analysis, behavior analysis like branch prediction, and some software vulnerability analysis just from these IR graphs. So we observed, and we also think that study the program and their IR, their representation as a graph is very promising. And if we can understand this better, or if a GNN can learn these intermediate graph representation better, it can largely benefit a lot of downstream tasks, whatever it is, right? So we really want to call for research in this area, that how can we design a better GNN to better represent the complicated IR graphs with loops, with different sizes, with different features, and then how can they be better equipped with downstream task predictions. Okay, so this is the end of the presentation. So today we talked about some graph representation power for programs, and we talked about some specific DN design for different, there might be some specific DN design opportunities for different downstream tasks, and also we're calling for benchmark development, because in this area, if we want to use machine learning, benchmark is always necessary. Okay, so this is the final, the summary. So we discussed the IronMan, and we discussed the program to circuit, and then we show the potential from program to circuit to program X, and we're looking forward to seeing more works in this area. So I think that's all for my talk, and thank you so much for listening.
Thank you, Cong. Thank you very much. Very impressive talk, and I learned a lot from your talk. So,
thank you.
Any questions from the audience? So if you have mute yourself.
Can I ask a question? Can I ask a question right now?
Sure.
I have a couple of questions regarding some details about the reinforcement learning. The first question is, so I saw your evaluation result. It's kind of the constraint, the user provided constraint is kind of some soft constraint, right? Or hard constraint.
You're asking the sorry, go ahead.
I saw the bar graph, and for constraint, the metric is kind of the percentage. I'm not quite sure if it is the hard constraint or a soft constraint.
I see. So currently it's a soft constraint, but we're putting a large penalty there.
Okay, so you encoded the constraint into the reward function, right?
That's right.
Okay, thank you. Another question is for the reward. So do you assign the reward for each action, or you assign the reward after the whole trajectory? I mean, is the reward sparse reward or dense reward?
Yeah, thank you for that question. Actually, I removed that description. The reward will only assign the reward at the last step after the entire graph is assigned. So it's very sparse.
Okay. So if it's a sparse reward, usually how long is the trajectory when you do the training? I mean, how long is the trajectory? The state action pair, how many in a trajectory?
So we will examine every node in the graph neural network once. So if you have 10 nodes, we examine these nodes 10 times, and then that's it. We examine those nodes one by one and determine whether we'll assign it or not.
Okay.
Does it?
Okay.
Yeah.
Okay. Also, the last question is, I remember you mentioned that you think the policy gradient is better than the actor created algorithm. So what kind of policy gradient algorithm you use? Is it vanilla policy gradient or some advanced one like PPO?
I believe it's, I need to check the details and then get back to you, but I believe it's straightforward reinforced policy gradient. It's a vanilla one, I believe. But I'm gonna need to check the more details, and then I can get back to you.
Sure, thank you.
Is that all right? Thank you. Yeah, thank you for being interested.
Thank you. Great work. Thank you.
Thank you.
Hello. Hello, Kevin.
Go ahead.
Sorry, excuse me. This is Jiafan. I graduated from Texas A&M University, and I used to work in Synopsys. Thank you for your presentation today. You summarized the three main challenges: the prediction, the multiple trade-off, manual code transformation. These three challenges are all the challenges I encountered during my work in Synopsys.
Okay, good to know.
Yeah, thanks. Very impressive presentation. So I have two questions. The first one is about the DSP constraints. Because my previous work is mainly in the ASIC-based compiler, so I'm not very familiar with this DSP constraint. I guess you are mentioning the FPGA-based compiler, right?
Right, right.
So can you briefly explain the DSP constraint? What does that means? I think.
Okay,
yeah, please go ahead.
Yeah. So thank you for the question. So yeah, this is work on targeting FPGA. So on FPGA, if you have a multiplication, it can be done either using the DSP. It's an embedded block to dedicatedly compute the multiplications or MAC operations. So we can either use this kind of resource to do the multiplication, or alternatively, we can use lookup tables. That's the logic to implement a multiplication.
Okay.
So that's typical in in FPGA. So maybe, for example, in ASIC, I'm thinking the DSP, the multiplication can be done using different multipliers. And also, if you want to design a logic, a different logic, I mean, different designs of a multiplier. You can think of it that way, I think.
Oh, so if I understand correctly, so I can understand the DSP and the LUT as two kind of resource, right? So they just...
Right.
Okay.
Right, exactly. Yeah. So backing to ASIC, it's just like two different multipliers.
Okay, I see. So, but then in your subgraph, yeah, exactly this page, the B, I think it's a little bit confusing. You show the DSP2, but you have 4 circles with yellow color, so it's a little bit confusing.
I see. In this case, these two can be reused. Yeah, and these two can be reused. I probably should mark it. Probably should annotate it. Thank you for reminding. Yeah.
Okay.
So these are reused. Thanks for reminding.
Okay, I see. Okay. Thanks for the question 1. And my second question is about the database. Yeah, my current work is related with your page 75. You say the extra. So I'm wondering, how can you get the database for your work?
So you're talking about
your whole work. You get you train your models. You need to feed your model with a bunch of data, right? And this data is the circuit designs. How can you create this circuit design? You manually create them, or maybe your circuit design is mainly in one. For example, it's only have one kind of feature. Maybe they mainly use the multiplication or something. So how can you guarantee the data sets is generalized?
This is a very good question. We get a lot of questions, and also we say criticized that how can we make sure our result can be representative or generalized to more more realistic cases, right? So this is also a major challenge that we observed, especially in the second paper, in the program to circuit paper. That first, the very naive is that we use synthetic graphs, that we just randomly generate a graph and we say, okay, this is addition, this is a multiplication. This is very easy to randomly create, right? And we use part of that to train. And then second, we create some synthetic programs in the program to circuit paper. So we create some synthetic programs. And these are, for example, they have loops, they have addition, they have multiplication, they have memory. So we extract their data flow graph from the compiler. So there's a IR in the compiler that can be extracted. So we extract those graphs, and then these graphs are training data, and then we synthesize those programs into the real implementation and get their ground truth. And yeah, so actually in the second paper, in graph to circuit program to circuit paper, almost all the training and evaluation are done on the synthetic programs. So they are real programs, but maybe they're not that representative for the real applications. So that's why we also tried to see how it generalized to these, for example, these ones, for some machine learning applications, for these matrix publications, for these applications, how well they generalize. And so far, it's not perfect, but it's promising. So maybe you can take a look at the program to circuit paper, and there are a lot of more detailed experimental results that you can see how well or how bad, you say, the GNN generalized from the synthetic program to real benchmarks. So I think that is indeed very worth investigating. So how can we make sure our synthetic program are representative for the real benchmarks?
I see. Okay. And the one quick question. So what's IR? Is short for what? The IR?
Intermediate representation.
I see. Okay. Thank you. I got it. I will
Sure.
go further search. Thank you. Thank you. Thank you so much.
Thank you.
Kelly. Thank you. That's it.
Hello, Kelly.
Hi, hello.
Kelly. Can you hear me?
Yes, I can hear you.
I have two questions to ask you. The first question is that you mentioned in your paper, you use an example in your paper that the IronMan behaves well when the boundary of the for loops is fixed. But I have a question that have you tried the IronMan in the situation that the boundary of the for loops is a variable? And I want to ask, will the IronMan behave well in this situation?
That is actually a very good question. So far, what we tried is to use fixed boundary loops. And in reality, if the loop boundary is variable, is there a way to fully unroll the variable boundary loop? So I think if the loop boundary is variable, in most cases, you just cannot unroll it, right? So if you cannot enroll it, it means it makes less sense to struggle for this sort of parallelism. But of course, you can do at some extent. But I think it's a direction that's worth investigating, and I think it will be interesting to study the variable boundary loop. But so far, we haven't considered it yet.
Okay, thanks.
But I think I indeed think that's worth investigating. Sorry, go ahead.
Yes, and my second question is about the code transformer. You mentioned that the code transformer will transform the original C code into another just for better performance. But I want to ask which form of the style you are going to transform to. I read the paper and I found that you seem to transform the code into a simpler one. For example, the original code is contains two operations. It's the sum and the multiply, and the transformed code is I found in the transformed code that each equation only contains one operation. So I mean, do you transform the code into a simpler one? I mean, you split the more complex operations into some simpler operations.
That is exactly, you get a very good point. So that is, I have to admit, that is one weak point of the current work. And we're definitely going to extend and to fix this. So currently, IronMan or the existing code transformation only works for the simplified situation with multiplication and addition. And I think it's very challenging if we want to handle more complicated cases like different types of operations, and especially when we're talking about memory, it's really complicated, and also with control signals. So my answer is, I'm sorry that currently we don't have a solution for the complicated code transformation scenario, but I think this definitely should be done in the near future, because that's the only way to make the overall flow or the overall approach applicable, practical in real cases.
Yes, I think the code transformation is very important in HLS. Yes, since
exactly.
Yes, I found in the experiment that different forms of code will lead to different results. So I think this is an area that need us to further investigate.
Exactly. That's why my next topic is just exactly code transformation. I'm thinking, is there a better way to do more hardware-friendly code transformation? And also, I think like Professor Hu just mentioned, this can be done in IR level. might be make things easier to do on IR level in a comparing to do that in source code level. So I think that's also a direction worth exploring.
Okay, thanks.
Thank you. I probably need to leave in 1 minute. I got a class to teach. So I think there is a question from the audience in the chat box. Someone is asking how many layers of GNN representation in the system. And because graph is similar to visual signals in CV, there are many layers. But okay, so in this case, we only used 2 layers of GNN, and that's we also did a study to show that 2 layers works that actually works the best. So here, these green ones are 2 layers, and then the 3 layers, 4 layers. So this is the error. So the lower the better. The 2-layer GCN works the best. So we are thinking that maybe the first reason is this graph is not that big, and then second, if we use multiple layers, there might be some over smoothing problem. But we didn't get a chance to look into the reason why it's only 2 layers works the best. But we did some exploration here. So yeah, that is also an interesting observation that we are calling for more insights here. That is it real the case that shallow GNNs are better for program representation? Thanks. And also a last question is how did we construct the graph, manually or something else? Okay, so the graphs are extracted from the the compiler, in the intermediate results of compiler. So it is extracted automatically, and those graphs are constructed into the adjacency matrix list, and this list will be fed into the training framework that can handle graph neural networks. Thank you. Thank you.
Okay, thank you again for your very wonderful talk and very detailed response to the audience questions. Also, thank you.
It's my pleasure.
Yeah, also thank everyone to attend our this week Rutgers seminar talk, and so see you next week. Thank you.
Bye. Thank you for the invite. Thank you. Bye-bye.
Bye.
Bye.